Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual history of physics is replete with moments of revolutionary insight, yet few documents articulate a discipline-altering question with the stark, forensic clarity of Tsung-Dao Li and Chen-Ning Yang's 1956 paper, Question of Parity Conservation in Weak Interactions. This work stands as a testament to the power of critical re-examination, a scholarly audit of a foundational principle that had been accepted more by habit than by proof. Its genius lies in its methodology, a systematic dismantling of the illusion of empirical certainty. The paper builds little new theoretical architecture instead. It performs an intellectual demolition, clearing the ground of a beautiful, symmetrical, yet ultimately unsubstantiated assumption. This essay will undertake a direct evaluation of the paper's internal claims, proceeding section by section through its argument to assess the logic, evidence, and profound implications of their inquiry. We will explore how Li and Yang, with surgical precision, isolated a fundamental ambiguity in the heart of particle physics and, in doing so, provided a direct and actionable roadmap for one of the 20th century's great experimental discoveries. Section 1, the introductory framing of a foundational doubt. The paper commences with a disarmingly simple premise, establishing a known landscape of fundamental symmetries. Li and Yang begin by affirming the robust experimental foundation for the conservation of parity in both strong and electromagnetic interactions. Parity, the principle of mirror-image symmetry, asserts that the laws of physics remain unchanged if all spatial coordinates are inverted, akin to viewing the world in a mirror. A process and its mirror-image process should occur with identical probability. The authors assert that the invariance of the Schrödinger equation under such a transformation, represented by the parity operator changing a position vector r to its negative, has been a cornerstone of quantum mechanics. Its eigenvalues of +1 or -1 define the intrinsic parity of a state, a conserved quantum number in these interactions. The author's claim here is rhetorical and strategic. They build a formidable edifice of established physics, a world of elegant symmetry, to create a stark backdrop for their central query. They establish parity conservation as a venerable principle, a law of apparent universality. The power of their opening argument is its immediate pivot. Having affirmed the law's dominion over two of the three known fundamental forces, they turn their attention to the third, the weak interactions responsible for processes like beta decay. Their core claim, presented with quiet force, is that upon close inspection, the assumption of parity conservation in this domain rests on a surprisingly fragile, almost non-existent, empirical footing. This section of the paper functions as an abstract for a revolution. It declares that a belief held by the entire physics community, from Pauli to Fermi, is an extrapolation, lacking direct experimental confirmation. The author's evaluation of the state of physics is that a fundamental law's universality had been accepted through intellectual inertia. Their argument is a profound challenge to the field's epistemological habits, suggesting that physicists had conflated the aesthetic appeal of symmetry with the rigor of empirical proof. Section 2, the tau-theta puzzle as an empirical impetus. The second section of the paper gives a concrete, pressing motivation for their abstract doubts. The famous tau-theta puzzle. Li and Yang present this anomaly as the immediate catalyst for their investigation. They detail the existence of a class of particles known as K-mesons, specifically focusing on two that were then designated as the Thameson and the Tormeson. The experimental evidence, they claim, pointed overwhelmingly to these two particles being one and the same. They shared, within experimental error, the same mass and the same lifetime. In the world of particle physics, mass and lifetime are the essential identifiers, the unique fingerprints of a particle. Any physicist observing these identical properties would naturally conclude they were observing a single type of particle behaving in different ways. Herein lay the paradox that Li and Yang so skillfully articulate. that the Thameson was observed to decay into two pions. The Tormeson, with the identical mass and lifetime, was observed to decay into three pions. The authors then proceed with their impeccably logical analysis of the parity states involved. A system of two pions, they argue, must possess a total parity of +1. This is derived from the intrinsic negative parity of each pion and considerations of their relative angular momentum. In contrast, a detailed analysis of the three-pion final state, as performed by the physicist Richard Dalletz, had shown that for the observed energy distributions, the three-pion system must possess a total parity of -1. The claim is stark if one accepts parity conservation in the decay process. Then the parent particle must transmit its own intrinsic parity to the final state. Therefore, that the Thameson, decaying to a positive parity state, must itself have positive parity. The Tormeson, decaying to a negative parity state, must have negative parity. The conclusion was inescapable. If the theta and tau were the same particle, as their mass and lifetime strongly suggested, then the single particle would need to possess both positive and negative intrinsic parity simultaneously, a logical absurdity. Li and Yang present this puzzle as a trilemma. Either parity conservation holds and the tau and theta are two different particles that happen to be mysteriously degenerate in mass and lifetime, or some error exists in the spin parity analysis of the decay products, or, the most radical possibility, the tau and theta are indeed the same particle, and the weak interaction responsible for its decay simply fails to conserve parity. This final option, they propose, would dissolve the paradox entirely. A single particle, the K-meson, could decay into two different final states with opposing parities if the decay interaction itself was indifferent to parity. This section transforms their general doubt into a specific, testable hypothesis grounded in a real-world experimental contradiction. Section 3. A systematic deconstruction of existing experimental evidence. The intellectual heart of Li and Yang's paper resides in their third section, a comprehensive and critical review of the experimental evidence concerning weak interactions. This is the core of their argument, where they move from posing a question to demonstrating its urgency by showing the complete absence of a prior answer. Their methodology is that of a meticulous audit. They categorize all weak interaction phenomena and scrutinize the experiments performed for each, asking a single, penetrating question: could this experiment have detected a parity-violating effect if one existed? A conclusion, delivered with the cumulative force of case after case, is a powerful negative. They begin with nuclear beta decay, the most studied of all weak processes. They analyze the typical experiments of the era, which measured two primary quantities: the shape of the energy spectrum of the emitted electrons and the decay rate, or half-life, of the nucleus. Their central insight is a brilliant piece of analysis concerning the mathematical character of the quantities being measured. Energy and decay rates are scalars. A scalar quantity is a single number that remains unchanged under a parity transformation. A mirror reflection. Li and Yang argue that if the fundamental interaction Hamiltonian, the mathematical expression governing the decay, contained both a scalar part that conserves parity and a pseudoscalar part that violates it, any experiment measuring only scalar observables would be constitutionally blind to the presence of the pseudoscalar term. The cross-term between the parity-conserving and parity-violating parts of the interaction vanishes when one calculates a purely scalar outcome. A pseudoscalar is a quantity that, like a scalar, is a single number, but it flips its sign under a parity transformation to reveal parity violation. They claim one must design an experiment that measures a pseudoscalar observable. Such an observable would have an expectation value of 0 if parity were conserved, while a non-zero measurement would be an unambiguous signal of its violation. As an example, they propose correlating the nuclear spin, which behaves as an axial vector. Its direction is defined by rotation and does not invert in a mirror, with the momentum of the outgoing electron, which behaves as a polar vector it does invert in a mirror. The dot product of an axial vector and a polar vector forms a pseudoscalar. No experiment, they declared, had ever measured such a correlation. They then extend this same exacting logic to the decays of other particles, pions, muons, and the so-called strange hyperons like the lambda and sigma particles. In each case, their analysis is the same. They examine the experimental literature and find that physicists had measured decay branching ratios, energy distributions, and angular correlations between outgoing momenta. All such measurements, upon close inspection of their transformation properties, yielded only scalar quantities. The search for a parity-sensitive pseudoscalar observable was consistently absent from the historical record. This section is a masterclass in theoretical physics as a critical tool. Li and Yang use the formal language of symmetry groups and tensor analysis to perform a deep critique of experimental practice. Their claim is devastating in its simplicity. For decades, the entire community had been looking for the weak interaction in rooms where the distinguishing evidence of parity violation was, by the very design of the experiments, impossible to. Section 4, a prescription for decisive experimental tests. Having demonstrated the complete lack of dispositive evidence, Li and Yang dedicate the fourth section of their paper to proposing a series of specific, practical experiments designed to fill the void. This transforms their critique from a purely theoretical exercise into a direct call to action for their experimental colleagues. The proposals are notable for their clarity and experimental feasibility. The most celebrated of these is the test involving the beta decay of a polarized nucleus. They suggest taking a sample of nuclei with a known spin, such as cobalt-60, and aligning these spins in a single direction using a strong magnetic field at very low temperatures to minimize thermal randomization. With the nuclear spins, which are axial vectors, or pointing in a known direction, one would then measure the direction of the emitted beta particles, or electrons. The electron's momentum is a polar vector. As previously argued, the correlation between the spin direction and the momentum direction is a pseudoscalar. If parity is conserved, the electron should be emitted isotropically, with no preference for direction relative to the nuclear spin. The mirror image of an electron emitted parallel to the spin axis is an electron emitted antiparallel to the spin axis. Symmetry demands these two outcomes be equally probable. A finding that more electrons were emitted, for example, in the direction of the nuclear spin than against it, would constitute a stark, unambiguous violation of mirror symmetry. The expectation value of the dot product of spin and momentum would be non-zero. They provided the blueprint for the experiment that would ultimately be performed by their colleague Qingxiang Wu and her collaborators at the National Bureau of Standards. Lin and Yang also proposed a second, independent line of experimental attack using the decay chain of a pion into a muon, which then decays into an electron. They argued that if the first decay violates parity, the resulting muon may be longitudinally polarized, meaning its spin would be aligned with its direction of motion. The subsequent decay of this polarized muon would then exhibit an angular asymmetry in its emitted electron. Measuring this asymmetry would provide another clean test. This section demonstrates their profound understanding of the interplay between theory and experiment. They did more than identify a problem, they engineered its solution. Their proposed tests were elegant because they were decisive. A positive result in any of them would suffice to overthrow a pillar of quantum mechanics. The intellectual integrity of this section is paramount. It shows that their question was a sincere inquiry into nature, backed by a concrete plan for obtaining an answer. Their claims were audacious, yet they were accompanied by a practical and verifiable path toward resolution, a hallmark of great scientific reasoning. Section 5, the concluding argument and intellectual stance. The paper's concluding remarks are brief and powerful, summarizing the force of their argument with an air of profound intellectual humility combined with unshakable logical conviction. They reiterate their central finding despite the firm belief in parity conservation. Its validity in the domain of weak interactions was entirely unsupported by any existing experimental data. They restate the author puzzle as the acute symptom of this underlying uncertainty, having systematically dismantled the illusion of knowledge and proposed a clear path forward. Their final claims address the theoretical implications with a certain intellectual austerity that itself makes a statement. They declare that they have no specific theory or model to propose that would explain why parity might be violated. They acknowledge that the idea of space having a handedness is a rather startling concept, yet they insist that the question of its conservation is one that can only be settled by experiment. This final posture is itself a crucial part of their argument's power. They resist the temptation to speculate on a deeper theory. By doing so, they keep the focus squarely on the empirical question. They sought to liberate the field from a beautiful but untested assumption, a form of intellectual idol. Their work was an appeal to a pure form of Popperian falsification, a principle, no matter how elegant or widely accepted, must be subject to the most stringent experimental tests imaginable. Their conclusion is a quiet challenge to the perceived hierarchy of physics, suggesting that a single, well-designed experiment could carry more weight than decades of collective theoretical assumption. The reception of their paper famously captured this tension. Some eminent physicists, Wolfgang Pauli included, initially expressed deep skepticism, finding the idea of a non-symmetric physical law aesthetically unpleasing. Yet the logic of the paper was inescapable, and its call to experiment was answered with remarkable speed. The successful execution of the Cobalt-60 experiment by Wu and her team in late 1956, confirming the dramatic asymmetry, vindicated Li and Yang's questioning in the most spectacular fashion possible. In conclusion, the 1955 paper by Tsung-Dao Li and Chen-Ning represents a watershed moment in the practice of theoretical physics. Evaluating its claims section, I-section reveals a work of extraordinary critical power, one whose primary contribution was the artful demolition of a false certainty. Its introductory framing set the stage by juxtaposing the known with the unknown. Its analysis of the author puzzle provided a tangible paradox demanding resolution. Its exhaustive audit of prior beta decay and meson decay experiments demonstrated a collective blind spot in the field's methodology, and its proposal of specific, decisive experiments provided an actionable path out of the confusion. The paper's internal logic is nearly flawless, proceeding from a general doubt to a specific anomaly, to a systematic critique, and culminating in a concrete research program. The work's enduring significance is a powerful lesson in scientific epistemology. It championed the primacy of empirical verification over aesthetic preference for symmetry. Li and Yang's great question did more than lead to the discovery of parity, violation, and a Nobel Prize. It served as a permanent reminder to the scientific community that the most deeply ingrained assumptions are precisely the ones that require the most rigorous and relentless questioning. It was a paper that, by asking a simple question about what was actually known, forever changed the conception of the physical universe itself.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.